where the universe unwinds slowly and curiosity drifts into dreams. Tonight, we're taking a calm, quiet journey to one of the strangest destinations in all of space, the heart of a collapsed star. These are the leftovers of brilliant giants, stars that lived gloriously, died dramatically, and left behind something so dense, so bizarre, and so quietly powerful that even time and space bend politely around them. Neutron stars, tiny, heavy, mysterious things that defy intuition and ignite wonder. So, wherever you are, maybe you're tucked under warm blankets, curled up on a couch, or floating in that pre-sleep space between thoughts. I hope this helps you ease into a restful state. If it doesn't lull you straight to sleep, well, at least you'll pick up some astrophysics along the way. I suppose that's the risk of making relaxing videos that are almost too interesting. If you're enjoying the journey already, I'd be ever so grateful if you gave this video a gentle like and perhaps subscribed so you don't miss the next cosmic bedtime story. I'd also love to know where in the world you're watching from and what time it is in your corner of the cosmos. Drop it in the comments if you're still awake by the end. Now breathe slowly, get comfortable. The stars have exploded, but all is calm. This video is for educational and relaxation purposes only. It is not intended as medical advice, diagnosis, or treatment. Please consult a professional for any health-related concerns, including excessive fascination with neutron stars. Long before a neutron star is born, before the collapse, before the cataclysm, before the crushing density, there is a cloud. A quiet, sprawling nursery made not of brick or stone, but of gas, dust, and the leftovers of other long-dead stars. These are stellar nurseries, and if you zoom out far enough they look like delicate wisps floating in the darkness. But inside, they're anything but still. Gravity is busy, very, very busy. A star begins not with a bang, but with a sag. Over time, particles in a molecular cloud begin to gather, drawn to each other by gravity's invisible pull. Imagine grains of sand rolling together slowly on a trampoline. More mass means more gravity, which means more attraction, which means even more mass. It's a feedback loop that ends with something glowing. Eventually, a core forms, a knot of matter that's dense enough and hot enough to ignite nuclear fusion. This is the magic that turns a clump of dust into a baby star. Hydrogen atoms smash together to form helium, releasing energy in the process. That energy pushes outward, fighting against gravity's inward pull. The result is a delicate balance, a star suspended between collapse and explosion, glowing gently in the vastness of space. But not all stars are created equal. Some are small and quiet, red dwarfs that simmer for trillions of years without much fuss. Others, like our Sun, live moderate lives, about 10 billion years of stable warmth and light. And then there are the giants. These massive stars, the future parents of neutron stars, live fast, burn hot and die young. They're dramatic, overachieving and, quite frankly, exhausting. To qualify for neutron star parenthood, a star needs to start off with at least 8 times the mass of our Sun. Some of them are dozens of times more massive. These stellar heavyweights go through their fuel like there's a cosmic deadline. They fuse hydrogen into helium, then helium into carbon, then carbon into oxygen, and on, creating heavier and heavier elements in their cores. Each stage burns faster than the last, like a candle flame being fed pure oxygen. Eventually the fusion chain reaches iron, and this is where everything changes. You see, iron is special. Unlike lighter elements, you can't extract energy by fusing iron atoms together. It just doesn't work. In fact, trying to fuse iron costs energy. So when a star builds up a core of iron, it's like reaching the end of a highway with no exits. The engine stalls, fusion stops, and with no outward pressure to counterbalance gravity, the star begins to fall inward on itself. But we'll get to that in another moment. let's linger just a bit longer on the life of a massive star because honestly, it deserves some appreciation. These stars are cosmic forges. Almost everything you're made of, the carbon in your DNA, the calcium in your bones, the oxygen you're breathing right now, was born inside a star like this, billions of years ago. Stars don't just light up the universe, they build it, and they do it with flair. Massive stars often end their lives in grand style, forming beautiful bubbles of hot gas, sculpting the interstellar medium, and sometimes forming binary systems with equally dramatic partners. They can spin rapidly, throw off enormous stellar winds, and even pulse in brightness as their internal dynamics shift and evolve. They're not so different from teenagers, really. Brilliant, unpredictable, and destined to change. But what makes one of these massive stars destined to become a neutron star instead of, say, a black hole? The answer lies in the delicate balance between mass and resistance. When the core collapses, it does so with astonishing speed, a fraction of a second faster than you can blink. Temperatures skyrocket to hundreds of billions of degrees. The outer layers of the star crash inward, slamming into the core, then rebounding outward in a powerful shockwave. This explosion is what we call a supernova, one of the most energetic events in the universe. It can briefly outshine an entire galaxy. If the collapsing core is not quite massive enough to become a black hole, but too massive to remain a white dwarf, it finds a strange middle ground. The pressure from all those neutrons packed together halts the collapse, at least temporarily, and what's left is a neutron star, a remnant about the size of a city, yet more massive than our sun. But we're getting ahead of ourselves. For now, just remember this. Stars are the great recyclers of the universe. They take simple ingredients, hydrogen, helium, and turn them into the stuff of planets, oceans, flowers, and people. They spend their lives quietly resisting gravity, only to be undone by it in the end. And in their final moments, they light up the universe with a brilliance that echoes across space and time. It's peaceful in a way, poetic. A star collapses and something new is born. Not quite alive, not quite dead, just different, quiet, dense, mysterious. So the next time you look up at the night sky, remember that some of those twinkling points are the calm survivors of ancient chaos. They've seen their suns die, their cores implode, and now they spin in silence, holding secrets heavier than anything on Earth. All of that from a simple cloud of dust. A star spends most of its life in a careful balancing act, performing an elegant fusion-powered dance that keeps it from collapsing under its own immense weight. But nothing lasts forever, not even in space. Eventually, for the universe's most massive stars, that delicate harmony unravels in a matter of seconds, and when it does, something truly spectacular happens. The star explodes. Tonight, we're easing into that dramatic finale, the supernova. Don't worry, we'll take it slow. For billions of years, a massive star burns like a furnace, converting lighter elements into heavier ones in a process known as nuclear fusion. It starts with hydrogen, the simplest and most abundant element in the universe. The star fuses hydrogen atoms into helium, releasing energy in the process. This energy pushes outward, keeping the star puffed up like a balloon against the relentless inward pull of gravity. But hydrogen doesn't last forever. When it runs low in the core, the star begins to fuse helium into carbon, then carbon into oxygen, then oxygen into neon, neon into magnesium, magnesium into silicon, and finally silicon into iron. Each step up the periodic table happens faster and faster. In the star's final days, these fusion processes might only last a few years, months, or even just days. And then it hits the iron wall. Iron is special in a frustrating kind of way. Unlike the lighter elements, you can't extract energy by fusing iron atoms together. Instead of releasing energy, fusing iron consumes it. It's like trying to power a light bulb by stuffing it with used batteries. Nothing happens, and everything just gets hotter and more unstable. Once the core of the star fills with iron, the fusion engine effectively shuts down. Gravity, which has been held in check for millions of years, suddenly has nothing to push back against. The balance breaks, and when that happens, the star begins to fall in on itself. Now this is where things speed up dramatically. In less than a second, the core begins to collapse. Temperatures soar to over 100 billion degrees. The pressure becomes so intense that electrons are forced into protons, creating neutrons and neutrinos. This process is called electron capture. It turns the core into a soup of densely packed neutrons, while a flood of neutrinos, nearly massless ghostly particles, escape in all directions. Imagine a bowling ball collapsing into a marble in the blink of an eye. That's the kind of scale we're talking about here. The core, once thousands of kilometers across, compresses into a dense sphere only about 20 kilometers wide, and in that same instant, the outer layers of the star, no longer supported by fusion, crash inward at a significant fraction of the speed of light. But this inward collapse doesn't go on forever. When the falling material hits the incompressible core of neutrons, it rebounds. It's like trying to crush a diamond with a pillow. The outer layers slam into an unyielding wall. This rebound, combined with the outward rush of neutrinos, creates a shock wave, and that shock wave punches through the collapsing star, blasting the outer layers into space in a cosmic detonation known as a supernova. A supernova is, frankly, absurd. For a brief period, a single exploding star can outshine an entire galaxy, made up of hundreds of billions of stars. The energy released in a few seconds is more than our sun will emit in its entire lifetime. If that sounds excessive, well, stars do love a grand exit. To an outside observer, this explosion looks like a sudden brightening in the sky, followed by a slow fade over weeks or months. But inside the star, it's chaos. Shock waves rip through the outer layers. The star's material is torn apart, scattered across light years. Elements forged in the star's core, carbon, oxygen, calcium, even iron, are flung into the cosmos. These elements will go on to form new stars, planets, and maybe even life. In fact, every atom of iron in your blood came from a supernova. Every bit of calcium in your teeth, every speck of oxygen in your lungs. That's the poetic part of stellar death. It's also cosmic recycling. The end of one star becomes the beginning of countless other things, but not all of the star is destroyed. At the heart of the explosion, something remains. If the original star was massive enough, at least 8 times the mass of our sun, the collapsed core will survive the blast, and depending on its exact mass, it will either become a neutron star or, if even more massive, collapse further into a black hole. But we'll save that darker path for another day. Let's linger with the neutron star. Right after the supernova, this newborn neutron star is incredibly hot, over 100 billion degrees, but it cools quickly, radiating away energy through neutrinos and light. It spins rapidly, often several times per second, and its magnetic field intensifies to unimaginable levels. In just a moment, the gentle fusion-powered glow of a living star is replaced with a dense, spinning magnetic corpse, packed tighter than anything else in the universe short of a black hole. From the outside, it's hard to grasp just how violent this process is, but if you were a neutrino, born in the heart of that collapsing core, you'd be ejected at nearly the speed of light. You'd pass effortlessly through the rest of the star, through the explosion, and keep going, through planets, moons, people, because neutrinos rarely interact with anything at all, and yet trillions of them pass through your body every second. That's not an exaggeration, it's a gentle, invisible truth of everyday life. The explosion also sends ripples through space-time itself. These are gravitational waves, subtle distortions in the fabric of the universe, radiating out from the dying star. We've only just begun to detect them in recent years, but they tell us stories that light alone cannot. Supernovae are rare in our galaxy, perhaps only one every 100 years, but their light can be seen across vast distances. Some of the most famous historical records of guest stars in the night sky were actually supernovae. Ancient astronomers from China, Japan, and the Middle East recorded bright new stars appearing for days or weeks before fading away. In one case, a supernova observed in the year 1054 left behind the Crab Nebula, still visible today through a telescope, and at its centre a pulsar, a spinning neutron star left behind by the explosion. From the calm to the catastrophic, the life of a massive star is a slow burn followed by an astonishing finale. For millions of years it held itself together, fusing elements and glowing steadily, and then, in its final moments, it collapses, explodes, and scatters its essence across the universe. It's strange, really, that such violence can lead to such beauty, that something so devastating can be the source of new beginnings. But the universe is full of these contradictions, explosions that create, deaths that give life, stillness born from fury. And at the centre of it all a small, dense remnant, quiet now, but full of secrets. When a massive star dies in a supernova, most of its outer layers are thrown violently into space, becoming part of the galactic tapestry, drifting gas clouds, raw material for new stars, maybe even the building blocks of future planets. But the core does something very strange. It collapses, yes, but then it stops collapsing. Not into a black hole, not quite. It lands in an in-between state, a bizarre state, and what's left behind is one of the universe's most extreme objects, a neutron star. So, what exactly happens in those chaotic final moments when a star folds in on itself? Let's imagine we could pause the universe just as the supernova is about to detonate. Let's zoom in, not on the explosion, but on the core, and what's happening at the smallest scale. The core of the star has become an iron ball, incredibly dense and under tremendous pressure. Iron, as we now know, can't be fused into heavier elements without consuming more energy than it gives off, so fusion stops. With nothing pushing outward, gravity takes over, and it does not take its time. In less than a second, gravity crushes the core inward. Atoms are smashed together so forcefully that the electrons, which normally whirl around the nucleus like excited children on a playground, are forced into the protons at the centre. This combination turns protons and electrons into neutrons, electrically neutral particles with no charge and very little personal space. This process is called neutronization, and it fills the collapsing core with, well, neutrons. Lots and lots of neutrons. It's like the entire core becomes one giant atomic nucleus, with the protons and electrons wiped away, leaving behind an ocean of pure neutron matter, the neutrinos, ghost-like particles created in this process. Burst out, carrying away huge amounts of energy. For a moment, this core is more dense than anything in the visible universe, hotter than the centre of a nuclear explosion, and somehow still not a black hole. The reason it stops collapsing, at least for now, is because of a strange kind of pressure. Not the kind you feel when you've got a deadline coming up. No, this is quantum pressure. More specifically, neutron degeneracy pressure. It's a consequence of the Pauli exclusion principle, a rule from quantum mechanics that says no two identical particles can occupy the same quantum state. In other words, neutrons don't like to be crowded. They push back, and that push is enough to stop gravity, unless there's too much mass, in which case, hello black hole. But if the mass is just right, somewhere between about 1.4 and 2.3 times the mass of our Sun, this neutron degeneracy pressure is enough to hold up the star's weight. And so, the collapse halts, the core stabilizes, the explosion continues outward, but at the centre something new has formed, a neutron star. Now let's pause and appreciate just how weird this object is. A neutron star packs more than the mass of the Sun into a sphere only about 20 kilometres wide. That's roughly the size of a small city. You could walk across it in a few hours if, of course, you could avoid being crushed, vaporized, or turned into subatomic mist. To put it another way, imagine taking a jumbo jet and compressing it down to the size of a sugar cube. That's the kind of density we're talking about. 1 cubic centimetre, about the size of a dice, would weigh as much as Mount Everest. And yet, this whole thing is sitting quietly in space, spinning, cooling, and occasionally flashing its magnetic beams like a celestial lighthouse. Inside the neutron star, things get even stranger. The outermost layer is called the atmosphere, though it's nothing like the air we breathe. It's a paper-thin layer of exotic plasma, where light and matter blur together in strange high-energy interactions. Beneath that is the crust. But don't let the word crust fool you. This is not a gentle outer shell. It's a layer of ultra-dense, super-rigid nuclear matter. At the top of the crust, you find nuclei packed tightly together, surrounded by a sea of electrons. As you go deeper, the pressure increases, forcing the nuclei into increasingly bizarre shapes. Scientists call these nuclear pasta. Yes, really. Because of their resemblance to spaghetti, lasagna, and other pasta-like forms. These structures are the result of nuclear forces battling gravity in a cosmic tug-of-war, and they're probably the strongest material in the universe. Below the crust is the core, and here things get speculative. We believe the outer core is a superfluid of neutrons, meaning the neutrons flow without friction. Imagine a liquid that never slows down, that doesn't splash, that behaves like it's from a sci-fi novel. That's the state of matter in the core of a neutron star. Go deeper still, and things become even more uncertain. Some theories suggest that the pressure might break down the neutrons into their constituent quarks, creating a soup of quark matter, a kind of ultra-exotic state that might exist nowhere else in the universe. Others believe the core might contain hyperons, strange particles with names that sound like comic book villains. The truth is, we don't know for sure. No laboratory on Earth can replicate these conditions. All we can do is observe, calculate, and wonder. One thing we do know, neutron stars spin, and they spin fast. The conservation of angular momentum, a fancy way of saying what spins keeps spinning, means that as the star collapses it spins faster and faster. Think of a figure skater pulling in their arms during a spin. A massive star that once rotated once every few days might, as a neutron star, rotate dozens, or even hundreds of times per second. These spinning neutron stars are called pulsars, and they emit beams of electromagnetic radiation from their magnetic poles. If those beams sweep past Earth, we see them as regular pulses, like a lighthouse beam in the night. Neutron stars also have magnetic fields, colossal ones. When the star collapses, its magnetic field intensifies, like squeezing a magnet tighter and tighter. Some neutron stars, known as magnetars, have magnetic fields over a quadrillion times stronger than Earth's. That's a 1 followed by 15 zeros. It's so strong that it could strip the information from a credit card from a distance halfway to the moon. Fortunately, magnetars tend to mind their own business and stay far, far away. All of this, the insane density, the crushing gravity, the exotic matter, the magnetic fury, is packed into a sphere the size of a city, hanging quietly in the cosmos. It's easy to forget that these bizarre objects started life as ordinary stars, fusing hydrogen in their cores, glowing softly, drifting along with their galactic neighbours, and now they sit as remnants, as relics, as testaments to the violence and wonder of stellar death. Neutron stars are strange, but they are also beautiful. They are compact records of physics at the edge, full of secrets we're only beginning to understand. They are the middle children of stellar evolution, not quite stars, not quite black holes, but with their own fascinating personality. And while they may seem distant, even alien, they are part of the same story we are. The iron in our blood, the calcium in our bones, all forged in the same fiery deaths that give birth to neutron stars. We are, in a very real way, made from the same stardust. And maybe, just maybe, that's why we find them so mesmerizing. A neutron star is small, just about 20 kilometers across. That's roughly the length of a leisurely morning drive through the countryside. But what it lacks in size, it more than makes up for in density. This is not just a heavy object. This is the heavyweight champion of the universe, short of black holes. It's a place where matter has been crushed so tightly that atoms no longer resemble anything we've ever seen on Earth. If the laws of physics had a basement, neutron stars would live in it. Let's start with the basics. Imagine scooping up a teaspoon of neutron star matter. Not a big ladle, just a gentle, dainty teaspoon. That single spoonful would weigh about 6 billion tons. That's roughly the mass of Mount Everest, crammed into something small enough to stir your tea with. Only, of course, you couldn't stir this matter. You couldn't even get close to it. It would drop straight through the planet, slicing clean through the mantle, core, and whatever else got in its way before exiting out the other side. Then it would probably continue falling through space, radiating menace and gravity in equal measure. But what is neutron star matter exactly? What happens to ordinary stuff, protons, electrons, atoms, molecules, when gravity goes completely overboard? Let's peel back the layers. Starting at the surface, we find a layer so thin it barely exists, the atmosphere. It's only a few centimeters thick and consists of plasma, a mix of electrons and nuclei, whipped into a frenzy by incredible gravity and magnetic fields. This air isn't the kind you'd want to breathe. It's hot, dense, and crackling with radiation. Light behaves oddly here. Because the gravitational field is so intense, photons trying to escape the star are redshifted, stretched into longer wavelengths, before they finally break free. Even colour takes a beating in this environment. Beneath the atmosphere is the outer crust. Now, crust might sound comforting, perhaps even edible. But this is no golden pastry. The outer crust of a neutron star is a layer of ultra-dense crystalline nuclei packed together like sardines in a sardine can. Only the can has been stomped on by an entire planet. These nuclei are surrounded by a sea of free electrons. The gravity is so strong here that if you dropped a marble from waist height, it would hit the surface at several thousand kilometers per second. That's fast enough to vaporize the marble, and quite possibly your waist too. Deeper still is the inner crust. Here the pressure is so great that electrons start merging with protons inside nuclei, turning them into neutrons. These neutrons begin to drip out, forming a sort of neutron-rich soup that coexist with nuclear clusters. It's a strange halfway place, part solid, part liquid, part question mark. Scientists call this the neutron drip region, and it's exactly as surreal as it sounds. And then we come to one of the weirdest parts of the neutron star, the pasta layer. No, this isn't a joke. Physicists, after working with brutally complex nuclear models for years, finally said, "Fine, it looks like spaghetti. Let's just call it that." And so they did. In this region, between the crust and the core, atomic nuclei arrange themselves into long rods, flat sheets, and blobs. Depending on the shape, they've been nicknamed spaghetti, lasagna, gnocchi, and even Swiss cheese. This isn't culinary whimsy. These structures emerge from the fierce competition between the strong nuclear force and gravity. The result is nuclear matter that's denser than anything on Earth and organized into some of the strangest shapes in the universe. And here's the wildest part. This pasta layer might be the strongest material known to science, over 10 billion times stronger than steel. If you somehow managed to forge a bridge out of neutron star pasta, it would withstand practically anything short of a black hole's hug. Moving inward, we reach the outer core. This is where things go from weird to our best guess. The density here is higher than anything you can create in a lab, so physicists rely on models, math, and the occasional prayer. Most agree that the outer core is made of a superfluid, a state of matter where neutrons move without resistance. Imagine a liquid that flows forever, never slowing down, never settling, and never clumping. A fluid so smooth that if you stirred it, it would spin in perfect silence forever. This superfluid neutron soup might also contain protons and electrons, although the protons would be in a superconducting state, allowing electric current to flow without resistance. These particles interact in ways that give rise to some of the neutron star's more exotic behaviours, like pulsar glitches, sudden changes in rotation that we'll get into a little later. For now, just imagine a star with the hiccups, and you're halfway there. Finally, we come to the inner core, and this is where things go delightfully speculative. Some theories suggest that at these crushing densities, several times the density of an atomic nucleus, neutrons can no longer remain intact. They may dissolve into their constituent parts, quarks. Quarks are the building blocks of protons and neutrons, and in a neutron star's core they might be set free, forming a soup of up, down, and possibly strange quarks. This hypothetical substance is called quark matter, and if it exists, it would represent an entirely new state of matter, never observed in a lab and only hinted at in cosmic observations. There are also theories that the inner core might host other exotic particles, hyperons, meson condensates, or even particles we haven't discovered yet. It's one of the biggest unknowns in astrophysics. We know what a neutron star does. We can measure its mass, its radius, its pulse. But we don't yet know what it is all the way down. What we do know is that neutron star matter doesn't behave like anything else. It's bound by gravity so strong that light struggles to escape. The surface gravity is over 200 billion times stronger than Earth's. If you stood on the surface, a dangerous idea for many reasons, you'd weigh several 100 billion times more than your normal weight. Even a single step would crush your bones, liquefy your organs, and compress your atoms into a shape that even your atoms wouldn't recognize. And yet, despite all this crushing pressure, neutron stars are among the most stable objects in the cosmos. They can persist for billions of years, slowly cooling, spinning, and pulsing as they go. They're like cosmic fossils, not dead exactly, but frozen in a state of extreme physics, waiting patiently for someone to figure them out. It's humbling to realize how much we still don't know about them. We've sent robots to Mars, we've mapped the DNA of countless species, we've split the atom and put telescopes in orbit, and still, when it comes to neutron stars, we're peering through a cosmic keyhole, guessing at what might be on the other side. But maybe that's what makes them so compelling. Not just their density or their strength or their impossible weirdness, but the fact that they challenge our understanding. They remind us that the universe is still full of mysteries, and that sometimes the smallest things, just 20 kilometers wide, can hold the biggest questions. So the next time you stir your tea, or pass a hill that vaguely resembles a teaspoon of Mount Everest, think of neutron stars. Think of the pasta layer. Think of the superfluid core, the crushed atoms, the unimaginable weight. And then exhale, knowing that, for now at least, the universe keeps these little monsters far, far away, nestled in the quiet corners of space, dense with secrets, and spinning in silence. Standing on the surface of a neutron star is not something you'd want to try, and not just because the travel arrangements are a bit inconvenient. The real issue is that physics itself becomes uncooperative the closer you get. Gravity, time, space. All the familiar rules begin to stretch, bend, and in some cases politely step aside while something stranger takes over. This chapter is all about what it means to exist near a neutron star, a place where gravity is so strong and space-time so warped that even light starts to question its life choices. Let's start with gravity, since that's the main character here. Gravity on the surface of a neutron star is, to put it mildly, intense. If you were somehow able to survive long enough to stand on it, which for the record you would not, you would weigh more than 200 billion times what you do on Earth. That's a 2 followed by 11 zeros. If you weigh 70 kilograms here on Earth, you would weigh about 14 quadrillion kilograms on a neutron star. You would be pressed down with such force that every atom in your body would be crushed beyond recognition before you could even think about saying ouch. But even though you can't visit one, we can still imagine what it would be like. The escape velocity, the speed you need to break free of a planet's gravity, is also completely unhinged. On Earth, escape velocity is about 11 kilometers per second. On a neutron star, it's around 150,000 kilometers per second. That's more than half the speed of light. If you wanted to launch a rocket from a neutron star's surface, you'd need fuel tanks the size of planets, and even then the rocket would probably melt before it got out of the gravity well. This immense gravity doesn't just hold on to matter, it also messes with light. When light tries to leave the surface of a neutron star, it has to climb out of an extremely steep gravitational well. As it does, it loses energy and shifts toward the red end of the spectrum. This effect is called gravitational redshift, and it means that if you are standing at a safe distance, looking at the light coming from a neutron star, it would appear redder and less energetic than it actually is. The star isn't changing colour, space-time is. This warping of space-time has another effect too. Time itself runs differently near a neutron star. The stronger the gravitational field, the slower time moves. This is a prediction of Einstein's general theory of relativity, and it's been tested and confirmed many times. On Earth we have to correct for this time dilation when using GPS satellites, but near a neutron star the effect is magnified to an almost surreal degree. If you could float just above the surface of a neutron star and somehow survive, time for you would pass more slowly than it would for someone far away. A minute for you might be several minutes for them. Over longer periods, this difference could be dramatic. A person spending what feels like a few years near a neutron star could return to find decades have passed elsewhere. It's not quite time travel, but it's the next best thing. And that's just what's happening to time and light. Space itself is distorted too. The intense gravity curves space so dramatically that objects behind the star can actually be seen around its edges. This phenomenon is called gravitational lensing, and it means that a neutron star, despite being tiny, can appear much larger than it actually is, like a funhouse mirror held up to the cosmos. Its gravity acts like a magnifying glass, bending the paths of light rays and letting us see the otherwise hidden regions of space behind it. These strange distortions make neutron stars incredibly useful for scientists. By observing the way light and time behave around them, physicists can test theories of gravity, probe the behavior of matter under extreme conditions, and explore the frontiers of astrophysics, all from a safe, respectful distance. Now let's imagine a thought experiment, just for fun and with zero risk of injury. Imagine you're in a specially designed space pod, the kind that ignores most known laws of physics for narrative convenience. You're floating just a few kilometers above the surface of a neutron star. Outside your pod, the star stretches below you, a perfectly spherical orb about 20 kilometers wide. It's not bright in the usual sense, but it's hot, incredibly hot. The surface temperature could be over 1,000,000 degrees Kelvin, though some older neutron stars cool down to just a few 100,000. Looking out the window, you'd notice something unusual. The horizon curves upward sharply. You can see more than half of the star at once, thanks to the gravitational lensing. If the neutron star had a glowing patch on its far side, you'd still be able to see it peeking around the edge, like taking a curved path to reach you. Time inside the pod ticks away slowly compared to the time back on Earth. Your watch still works, but when you compare notes with mission control later, you'll find that your few hours up here translated to several hours or even days down there. You've effectively skimmed through time, like skipping a stone across a pond made of gravity. Outside, magnetic fields swirl with unimaginable strength. Some neutron stars, especially the magneteas, have magnetic fields so intense they could strip electrons off atoms from thousands of kilometers away. The field lines whip and twist, and you can almost imagine them humming, though in the vacuum of space there's no sound. Still, your pod vibrates slightly as charged particles from distant space interact with the magnetosphere. Even the vacuum isn't truly empty here, and then from somewhere deep below, a sudden glitch. The neutron star's spin skips a beat. This is not a malfunction, but a real phenomenon, a starquake. The crust, under enormous tension, shifts suddenly, releasing pent-up energy and altering the star's rotation by a tiny fraction. It's like a hiccup from a star that's been holding its breath for 10,000 years. To your instruments, it shows up as a sudden change in pulse timing, a blip in the rhythm of the universe, and just like that, the glitch is over. The spin continues, the pulses resume. The neutron star goes back to pretending it's just a peaceful, quiet little thing, rather than a collapsed core of screaming gravity and matter compressed into near-mythical densities. Your pod rises, gravity loses its grip, space flattens, time normalizes, and Earth calls you home, back to a planet where standing still doesn't compress your atoms, where light travels in straight lines, and where gravity is thankfully a bit more polite. Of course, all of this is just imagination. In reality, no pod could survive that close. No human could endure the radiation, the pressure, the temperature. But even at a safe distance, neutron stars exert their influence. They pull at our equations, our telescopes, our imaginations. They show us what happens when the universe pushes matter to its limits and asks, what now? What happens is astonishing. Space bends, time slows, atoms surrender, and something stable, silent, and endlessly strange is left behind. Neutron stars remind us that the cosmos doesn't need to be large to be powerful, that the tiniest points of light can hide the deepest wells of gravity, and that even in collapse, the universe creates something remarkable. When neutron stars spin, they don't just sit quietly like cosmic pebbles, they flash, they blink, they beam, and from across the galaxy we see these pulses with the regularity of a ticking clock. That's why we call some neutron stars pulsars, short for pulsating radio source. But don't let the name fool you. These aren't flickering candles. They are the lighthouses of the universe, and their beams are powered by some of the most extreme physics imaginable. Let's rewind for a moment. When a massive star collapses into a neutron star, it doesn't just shrink, it spins. This is due to a principle in physics known as the conservation of angular momentum. It's the same effect you see when a figure skater pulls in their arms and spins faster. As the mass of the star collapses inward, its rotation speeds up dramatically. A star that originally took days to rotate once may now spin dozens or even hundreds of times per second. That might sound fast, and it is. But the truly mind-bending part is how stable this spin can be. Pulsars rotate with astonishing precision. Some of them keep time better than the most accurate atomic clocks on Earth. If you had a pulsar on your wrist, ignoring the small matter of it weighing more than the moon, you could tell time more reliably than with anything humans have ever built. Now, not every neutron star is a pulsar. To be a pulsar, a neutron star has to meet two conditions. It needs to have a strong magnetic field, and it needs to be spinning at a decent clip. The combination of spin and magnetism creates a powerful electric field, which rips charged particles from the surface and accelerates them along the magnetic poles. These charged particles emit beams of electromagnetic radiation, usually in the radio spectrum, though sometimes in visible light, X-rays, or even gamma rays. But here's the key. The magnetic axis is usually not aligned with the rotation axis. That means as the neutron star spins, its beams sweep through space like the light from a lighthouse. And if one of those beams happens to cross Earth, we see it as a regular pulse. Hence, pulsar. The first pulsar ever discovered was found in the late 1960s by Jocelyn Bell Burnell, who at the time was a graduate student working on a radio telescope. She noticed a regular, repeating signal, a pulse occurring every 1.3 seconds. It was so regular, in fact, that the team briefly considered the possibility of it being an artificial signal. They jokingly labelled it LGM1, short for Little Green Men. But soon, other similar signals were found, and the true nature of pulsars began to emerge. No aliens, just very, very punctual dead stars. That first pulsar still spins today, like a heartbeat frozen in time, and we've since found thousands more, each with its own rhythm and personality. Some pulsars spin slowly, once every few seconds. Others known as millisecond pulsars, spin hundreds of times per second. The fastest one known spins over 700 times per second. Imagine something the mass of the sun spinning that fast without flying apart. The only reason it holds together is because of its immense gravity. If a neutron star were any less dense, it would tear itself to pieces. Millisecond pulsars are particularly interesting because many of them are thought to have been recycled. That is, they were once ordinary pulsars that slowed down over millions of years. But then, they picked up some extra speed by stealing matter from a nearby companion star. As material spiraled onto the neutron star, it transferred angular momentum, like pushing a merry-go-round, and the neutron star spun faster and faster. These cosmic vampires have an eerie elegance to them, sipping from their neighbours and silently accelerating to ridiculous speeds. Despite their terrifying density and incredible power, pulsars are surprisingly useful. Astronomers use them as natural cosmic clocks. By measuring the arrival time of their pulses, we can detect incredibly subtle phenomena, like the tiny wobbles caused by orbiting planets, or the stretching of space-time itself due to gravitational waves. There's even been talk of using pulsars for spacecraft navigation. Imagine future explorers travelling through deep space, using a map made of dead stars to guide their way. Some pulsars have companions, white dwarfs, or even other neutron stars, and orbit around them in tight, complicated dances. These systems are especially valuable because their gravitational interactions reveal a wealth of information. For example, the famous Hulse-Taylor binary pulsar provided the first indirect evidence for the existence of gravitational waves. As the two neutron stars orbited each other, they slowly spiraled inward, exactly as predicted by Einstein's general theory of relativity. The system lost energy not through light, but through ripples in space-time. That discovery earned a Nobel Prize and paved the way for the gravitational wave detectors we use today. And then there are pulsar glitches. Every now and then, a pulsar that's been spinning steadily for thousands of years will suddenly speed up, just a little. These glitches are thought to be caused by starquakes, shifts in the rigid crust of the neutron star, or by interactions between the superfluid interior and the solid outer layers. Whatever the cause, it's like the neutron star stumbles and quickly recovers, slightly faster than before, a cosmic hiccup if you like. Pulsars also play a role in some of the most violent events in the cosmos. When two neutron stars spiral into each other and merge, a process that takes hundreds of millions of years, they can produce a burst of gravitational waves, a brief flash of gamma rays, and a kilonova explosion. These are rare events, but when they happen, they light up the universe and create heavy elements like gold and platinum. The death of pulsars can, quite literally, result in treasure. But perhaps the most astonishing thing about pulsars is just how calm they are. On paper, they are absurd. City-sized spheres of degenerate matter, spinning at hundreds of revolutions per second, radiating energy through immense magnetic fields, and pulsing across the galaxy. And yet, from Earth, they arrive as steady, soothing beacons, like metronomes keeping time in the vast silence of space. Some emit pulses that are so regular, we can predict their timing to within a millionth of a second. They remind us that even in the chaotic dance of galaxies and dark matter, there are rhythms, reliable patterns, quiet pulses in the dark. In a way, they're the perfect bedtime companions, not noisy or explosive, just gently persistent. A tap, a beat, a flicker in the night sky. You may never see one with your eyes, you may never hear its call, but out there, across the emptiness, a neutron star is spinning. Always. Just as it has for millions of years, and just as it will for millions more, tick, 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 some neutron stars, as if being dense, tiny and wildly fast weren't enough, go even further. They take their already extreme properties and crank them up into the realm of the ridiculous. These are the magnetars, neutron stars with magnetic fields so powerful they make ordinary neutron stars look like fridge magnets. In a universe full of wild phenomena, magnetars are the ones that leave even seasoned astrophysicists blinking in quiet awe. To understand what makes magnetars so special, let's begin with the basics of magnetism. Every neutron star has a magnetic field. It's a byproduct of the star's rotation and the way charged particles move within and around it. Even a typical neutron star, the normal kind, might have a magnetic field trillions of times stronger than Earth's. That's already enough to cause problems for anything that might wander too close. But magnetars take this to an entirely different level. Their magnetic fields can be over 1,000 times stronger than those of regular neutron stars. In numbers, we're talking about magnetic fields of around 1 quadrillion Gauss. That's a 1 followed by 15 zeros. Earth's magnetic field, for comparison, is around half a Gauss. So a magnetar's field is not just strong, it's borderline absurd. It's so strong that if one were placed at a distance equal to the moon, it could erase your credit card. That's not poetic exaggeration. That's just physics being terrifying. The magnetism of a magnetar is so intense that it affects the very fabric of the vacuum around it. In these fields, quantum electrodynamics kicks in, and the vacuum becomes birefringent, a fancy way of saying that empty space starts to behave like a lens, bending light differently depending on its polarization. This has actually been observed by astronomers looking at the light from a known magnetar, confirming that these effects are not just theoretical musings, but real phenomena happening hundreds or thousands of light years away. So how do magnetars form? The current thinking is that they are born from especially massive stars that collapse with an unusually rapid spin and a particularly high internal magnetic field. During the core collapse, as the star's volume shrinks dramatically, magnetic field lines are compressed, like winding up a coil. This amplifies the magnetic field to monstrous levels. The result is a magnetar, a dense, spinning neutron star with a magnetic field that could tear apart atoms from a distance. But here's the interesting twist. Magnetars don't spin very fast for long. Their intense magnetic fields create strong drag forces, which quickly slow their rotation. Most magnetars spin only once every few seconds. Sluggish, by neutron star standards. That's still faster than your average turntable, of course, but much slower than millisecond pulsars. The energy they lose through magnetic braking gets dumped into their surroundings, heating the star's surface and fueling bursts of high-energy radiation. And that's where things get really dramatic. Magnetars are known for their outbursts, sudden, intense flares of X-rays and gamma rays. These flares can release more energy in a single second than the sun emits in 100,000 years. Some of them are so powerful that they can be detected across the entire galaxy. Others are more subtle, soft gamma-ray repeaters that flare quietly, like a sleeping dragon occasionally snorting fire. The most powerful magnetar flare ever recorded happened on December the 27th, 2004, from a magnetar about 50,000 light-years away. For a fraction of a second, it was the brightest thing in the sky aside from the sun. If that flare had happened within 10 light-years of Earth, it could have seriously damaged our atmosphere. Fortunately, it didn't. Space is big, and magnetars, while dangerous, tend to keep their distance. These outbursts are thought to be caused by starquakes. Yes, you heard that right. Starquakes. Just like Earth's crust can shift and crack during an earthquake, the rigid crust of a neutron star can suddenly snap under the strain of the intense magnetic field. This releases a tremendous amount of energy, often accompanied by a shift in the magnetic field itself. Imagine the crust of a star, packed tighter than anything you can imagine, suddenly cracking with a snap that sends ripples through space-time. That's a magnetar starquake. These events are not just fascinating, and they're scientifically useful. The energy from magnetar flares travels through space and can interact with other objects. They can trigger reactions in nearby gas clouds, influence star formation, and even give us clues about the structure of space itself. By studying them, astronomers can probe conditions that are impossible to recreate on Earth. Magnetars become, in essence, natural laboratories for high-energy physics and quantum mechanics. One of the strangest things about magnetas is that despite all their fury, they live relatively short and quiet lives. After about 10,000 years, which in cosmic terms is like the blink of an eye, their magnetic fields weaken, their flares subside, and they begin to fade into the background, becoming more like ordinary neutron stars. Their time in the spotlight is brief but unforgettable. Astronomers have identified only a few dozen confirmed magnetars, though there are likely many more hidden across the galaxy, too faint or distant for us to detect. Some are found in the aftermath of supernova. Others sit quietly in star-forming regions, lurking like sleeping giants. We've even detected fast radio bursts, sudden, intense bursts of radio waves from deep space that might be linked to magnetar activity. The mystery deepens. Because of their unique characteristics, magnetars sometimes show up in science fiction. They're the villains of neutron star stories, powerful, unstable, and unpredictable. But like many things in the universe, their real story is more nuanced. Yes, they're powerful. Yes, they're dangerous. But they're also surprisingly fragile, cracking under their own magnetic stress, fading quickly compared to their more stable siblings, and spending most of their lives in eerie silence. Imagine being near one. Not too near, of course. From a safe distance of several light years, you might see it as a faint source of high-energy radiation. You wouldn't hear it, but if it flared, you might see a sudden, brief spike of light on your instruments. It would flash and fade in less than a second, leaving your sensors buzzing and your software asking, "What was that?" And that's how it goes with magnetars. They arrive with a bang, spin down with a sigh, and vanish into the night like cosmic ghosts. But in their brief lives, they show us the raw, unfiltered power of the universe. They're a reminder that nature doesn't need size to be terrifying, just density, magnetism, and the occasional catastrophic temper tantrum. Yet there's something oddly peaceful about them too. After the flares, after the bursts, after the cracks and quakes, magnetars settle. They spin slowly, they cool, they fade, they become quiet again, and somewhere in the galaxy, one of them might be doing just that, right now, flaring silently in the darkness, twisting magnetic fields like spaghetti, and bending light itself with a shrug of its magnetic shoulders. Magnetars are not monsters. They are masterpieces, strange, brief, and unforgettable. Neutron stars may appear still from a distance, those steady pulses, those elegant spins, but on the inside, they're anything but calm. Beneath the crust, deep inside these cosmic pressure cookers, something stirs, something shifts, and every so often it causes the star to twitch. A sudden change, a momentary hiccup in the rhythm of the universe. These strange interruptions are called glitches, and they are the result of forces so exotic they might as well be from science fiction. But before we dive into the strange world of neutron star glitches and starquakes, let's take a moment to appreciate just how remarkably steady these stars normally are. Pulsars, the spinning neutron stars that beam radio waves toward Earth, are famously reliable. Some of them rotate hundreds of times per second, with such consistency that astronomers use them as cosmic clocks. In fact, a few pulsars are so regular that if you compared their pulses to an atomic clock, the differences would be measured in microseconds over years. But every now and then the pulse skips a beat. Or rather, it doesn't skip, it speeds up. Ever so slightly the star's rotation rate increases. Not by much, usually just a few parts in a million. But it's enough for astronomers to notice. It's enough to raise questions. Because in the universe, objects that spin are supposed to slow down over time. Friction, radiation, and magnetic drag all act to gradually reduce the rotational speed of neutron stars. So when one speeds up, even slightly, something strange is happening. These sudden speed-ups are called pulsar glitches. They were first discovered in the late 1960s when astronomers noticed that the Vela pulsar, a young neutron star about 1,000 light-years away, suddenly began spinning slightly faster, and since then similar events have been observed in dozens of other pulsars. So what's going on? To understand glitches, we have to take a peek beneath the crust of the neutron star. Now, this crust isn't like the one under your feet. It's far stronger, far denser, and under pressures billions of times greater than anything on Earth. But even this supercrust has limits. Over time, as the star spins and its internal dynamics shift, stress builds up in the crust, especially in the region where it connects to the star's inner layers. Eventually, something's got to give. One possible cause of a glitch is a starquake. Just like Earth has earthquakes, neutron stars can experience sudden shifts in their crusts. The intense pressure causes a crack, a break, or a sudden rearrangement. The crust snaps ever so slightly inward, and because this shifts mass close to the axis of rotation, the star speeds up, like a spinning ice skater pulling in their arms. The rotation rate increases, and the pulses arrive just a little earlier than expected. Another explanation, one that digs deeper, involves the superfluid interior of the neutron star. Beneath the crust lies a layer of neutron-rich superfluid, a bizarre state of matter that flows without any resistance. It's frictionless, silent, and very, very particular about how it behaves. This superfluid doesn't spin in the normal way. Instead, it forms tiny whirlpools called quantized vortices, each carrying a tiny bit of angular momentum. These vortices anchor themselves to the crust, but over time they can get pinned in place. As the outer crust slows down from radiation loss, the inner superfluid keeps spinning at its original speed. The tension between these two layers builds, like winding a spring. Eventually the vortices unpin all at once. In a fraction of a second, the stored angular momentum transfers to the crust, causing the star to spin slightly faster. And just like that, a glitch occurs. It's a cosmic slip and release mechanism, like popping the lid off a tightly wound jar, only instead of peanut butter, it's nuclear matter and space-time. Both models, crustal starquakes and superfluid vortex unpinning, likely play roles in different kinds of glitches. Younger neutron stars, which tend to glitch more often, might be more prone to crustal shifts. Older, cooler neutron stars may experience more superfluid dynamics. The truth is, we're still learning. Glitches are one of the only windows we have into the deep interiors of neutron stars. Every one we detect is a clue. What makes these glitches even more fascinating is how quickly the star recovers. After a glitch, the spin rate doesn't just stay at its new value forever. It usually relaxes, slowly drifting back toward the pre-glitch rate over days, weeks, or even months. The star's interior seems to remember its original rhythm and tries to get back to it, like a music box winding down. And here's a curious thing. Sometimes the glitch is accompanied by changes in the star's pulse profile, the shape of the beam we see from Earth. That suggests that something more than just rotation is shifting. Maybe the magnetic field is twitching, maybe the crust is deforming, maybe the whole star is subtly rearranging itself in a process we still don't fully understand. There's something deeply poetic about that, isn't there? A star, a dense remnant of something long dead, still capable of shifting, of quaking, of changing. Not just a frozen relic, but a living machine full of tension and movement, creaking under the strain of its own existence. Glitches aren't just a curiosity, they have practical uses too. By studying the timing of glitches, scientists can learn about the structure of neutron stars, things like the strength of their crusts, the behavior of superfluid matter, and even the configuration of their internal magnetic fields. It's like watching a cracked bell ring and learning everything about the metal inside from the sound it makes. And then there's the rarest, most mysterious kind of glitch, the anti-glitch. Instead of speeding up, the neutron star suddenly slows down. This has only been observed a handful of times, and we're still not quite sure what causes it. Perhaps a magnetic field reconfiguration, or a sudden change in the interaction between the crust and the superfluid. Whatever it is, it's another reminder that neutron stars are full of surprises. They may seem like cosmic clockwork from a distance, blinking in perfect time, spinning with robotic regularity, but inside they are full of stress, tension, and sudden jolts they creak, they twitch, they remember, they adjust. It's strange to think of stars having such personalities. Yet the more we study them, the more we realize that neutron stars are not just extreme, they're expressive. Their glitches and quakes are like sighs from something ancient and immense, whispering through the vacuum of space. And so, we watch, we listen. We wait for the next tiny tremble from a star that spins in silence, carrying the memory of its collapse and the weight of forces we're only beginning to understand. Neutron stars are by their very nature invisible. They don't glow brightly like ordinary stars, and they don't have swirling clouds of gas like planets or nebulae. They're small, dense and dark, more shadow than light. And yet somehow we've learned a great deal about them. We've studied their pulses, mapped their magnetic fields, and even detected the ripples they make in space-time. But how? How do you study something you can't see? The answer lies in the many ways a neutron star leaves fingerprints on the universe. Although they're physically small and visually quiet, neutron stars make noise in all the other cosmic languages: radio waves, X-rays, gamma rays, and even gravitational waves. With the right instruments and a bit of patience, we can pick up their signals and start to piece together their stories. Let's begin with the most famous method: radio telescopes. This is how neutron stars were first discovered. Back in the 1960s, large radio dishes were scanning the skies when astronomers noticed a repeating signal. It was regular, steady, like a clock ticking in the dark. That signal turned out to be a pulsar, a neutron star emitting beams of radio waves from its magnetic poles. When these beams sweep past Earth, they appear as regular pulses, and because neutron stars spin so predictably, those pulses can be timed with incredible precision. By watching the arrival times of these radio pulses, scientists can determine a neutron star's rotation rate, how fast it's slowing down, and whether it's orbiting another object. We can even detect tiny wobbles in its spin, hints of internal changes or nearby gravitational influences. Radio observations also help us map the structure of the neutron star's magnetosphere, the bubble of magnetic activity around it. Changes in pulse shape and brightness tell us how particles are moving through this region, giving us indirect clues about the star's magnetic field and surface conditions. But not all neutron stars are radio loud. Some are quiet in radio wavelengths but scream in X-rays and gamma rays. These higher energy forms of light require space-based telescopes, like NASA's Chandra X-ray Observatory or ESA's XMM Newton. These instruments float high above the Earth, safely beyond the atmosphere, which absorbs most X-rays before they can reach the ground. From orbit, they can watch as neutron stars emit bursts, flares, and steady streams of X-rays. Many of these emissions come from accreting neutron stars, that is, neutron stars pulling in matter from a nearby companion star. As this material falls inward, it heats up, sometimes to millions of degrees, and glows brightly in X-rays. In binary systems, this can lead to dramatic events: flickering, spinning, or even sudden flares of light as matter crashes onto the neutron star's surface. X-rays are also used to study magnetars, which occasionally emit powerful outbursts of energy. When these stars flare, they release intense streams of high-energy radiation, and X-ray telescopes are often the first to catch them in the act. The light curves, graphs of brightness over time, help scientists understand what's happening inside the star when it glitches, flares, or cracks under pressure. Then there are the truly high-energy messengers, gamma rays. Some pulsars, especially younger or more energetic ones, emit beams of gamma rays from their magnetic poles. These are the most energetic photons in the universe, and we detect them using special telescopes like the Fermi Gamma Ray Space Telescope. Unlike radio or X-rays, gamma rays can pass through many obstacles, but they're rarer and harder to catch. Still, when we do detect them, they tell us a lot about how particles are accelerated in the fierce environments of a neutron star. In recent years, we've added a brand new tool to our observational toolbox, one that doesn't involve light at all. This is the era of gravitational wave astronomy. Gravitational waves are ripples in space-time caused by the acceleration of massive objects. Albert Einstein predicted them over 100 years ago, but they weren't directly detected until 2015, when two black holes collided and sent a ripple through the cosmos that reached Earth. Since then, we've also observed neutron star mergers using gravitational waves. In 2017, scientists detected a signal that came not from black holes, but from two neutron stars spiraling together and colliding. The event, called GW170817, was historic. Not only did it produce gravitational waves, but it also emitted light, X-rays, gamma rays, and visible light, all of which were detected by telescopes around the world. This was the first time in human history that we had observed the same cosmic event, both with light and with gravitational waves. It was like hearing and seeing something at the same time, giving us a richer, fuller understanding of what had occurred. From that single event, we learned that neutron star collisions produce kilonovae, bright explosions that forge heavy elements like gold and platinum. We also confirmed that these mergers can create black holes, release gamma ray bursts, and stir up space-time like a spoon in a galactic teacup. Even more recently, astronomers have begun to use fast radio bursts, or FRBS, to learn about neutron stars. These are mysterious, extremely brief pulses of radio waves that come from distant galaxies. Some of them repeat, others don't. And while we still don't know exactly what causes them, one repeating FRB was traced back to a known magneta, providing strong evidence that at least some FRBs come from the magnetic tantrums of neutron stars. There's even hope that neutrinos, those nearly massless particles that fly through everything, might one day help us study neutron stars more directly. Neutron stars produce vast numbers of neutrinos during their formation in supernova, and while detecting them is difficult, future observatories might be able to catch more of them in action, giving us a view of the inner workings of stellar death. It's worth pausing for a moment to appreciate how incredible this all is. We are tiny creatures on a rocky planet, spinning around a modest star in one corner of one galaxy, and yet we've built tools that let us study the remains of dead stars thousands, even millions, of light years away. We can't touch neutron stars, we can't land on them or scoop up samples, but we can listen, we can watch, we can detect their faint pulses, their sudden flares, their gravitational echoes. We've come a long way from the days when all we had were our eyes and a few glass lenses. Now we have an entire orchestra of instruments, radio, X-ray, gamma ray, gravitational wave, neutrino, all playing in harmony to tell us the stories of these distant cosmic relics. Neutron stars don't show themselves easily. They hide in darkness, whisper through the void, and leave only the faintest of signatures behind. But when we tune in carefully enough, we discover that they've been speaking to us all along, in radio pulses, in flickers of light, in the stretch and squeeze of space-time itself. And perhaps the most beautiful part is that there's still so much we haven't heard yet, so many signals still drifting our way. All we have to do is keep listening. Neutron stars spend most of their lives alone, spinning quietly, flashing their steady pulses into the dark. But sometimes, just sometimes, they find a partner. Another neutron star perhaps, or a massive star that has yet to collapse. And when these companions orbit close enough, a dramatic fate begins to unfold. Over millions, even billions of years, their orbits shrink, their dance quickens, and eventually the two objects collide. When this happens, the universe doesn't just watch, it celebrates, with a spectacular explosion known as a kilonova. Let's walk through how we get there. Imagine two neutron stars orbiting each other. Maybe they were once part of a binary star system, two massive stars that both went supernova and became neutron stars. If they remained gravitationally bound, they would continue orbiting around their common centre of mass, gradually spiralling inward. This inward motion is caused by the emission of gravitational waves, ripples in the fabric of space-time itself. Every orbit sends out a little pulse of gravitational energy, stealing just a bit of momentum from the system. Over immense periods of time, these ripples slowly drain energy from the orbit, tightening the spiral. The two stars draw closer and closer, their orbits quicken, years become months, months become days, and eventually they whirl around each other many times per second, screaming silently through the cosmos, and then they merge. When they do, the result is one of the most extreme events the universe can produce, a cataclysm of density, gravity, and light. The collision of two neutron stars unleashes a flash of gamma rays, a shower of gravitational waves, and a glowing, radioactive explosion known as a kilonova. Kilonovae are a special kind of supernova, not quite as luminous as the core collapse explosions that create neutron stars, but vastly more powerful than most other types of stellar outbursts. They shine 1,000 times brighter than a typical nova, hence the name kilonova. But brightness isn't even the most interesting part. Kilonovae are also factories for the heaviest elements in the universe. Gold, platinum, uranium, these don't form in ordinary stars. The nuclear fusion processes inside stars can only build elements up to iron. Anything heavier than that needs extreme conditions, massive energy, dense neutron-rich environments, and rapid neutron capture. And that's exactly what a neutron star collision provides. When the two stars collide, chunks of ultra-dense neutron-rich matter are ejected into space. As this matter cools and expands, it undergoes a process called R-process nucleosynthesis, or rapid neutron capture. In this process, atomic nuclei absorb neutrons faster than they can decay, building up into heavier and heavier elements in just seconds. When the dust settles, what remains is a cloud of newly minted heavy elements, drifting through space and eventually becoming part of future stars, planets, and people. Yes, if you're wearing a gold ring or have a bit of platinum in your electronics, that material may very well have been forged in the merger of two neutron stars billions of years ago. Somewhere, deep in the universe, a collision happened, and atoms from that explosion eventually found their way to Earth. We've known about this process in theory for a long time, but we didn't have direct evidence of it until 2017. That year, gravitational wave observatories detected a signal named GW170817, a ripple in space-time caused by the merger of two neutron stars about 130 million light-years away. Just seconds later, a burst of gamma rays was detected. Then telescopes around the world sprang into action, looking at the patch of sky where the signal came from. What they found was a faint glowing object, a kilonova. Over the following days, astronomers observed the light change in brightness and colour. As the explosion cooled, the spectral signatures of heavy elements appeared. It was the smoking gun, direct proof that neutron star mergers create gold, platinum, and other R-process elements. This event was a landmark in modern astronomy. It was the first time we observed the same cosmic phenomenon in multiple ways: gravitational waves, gamma rays, visible light, X-rays, and radio waves. It marked the dawn of what scientists call multi-messenger astronomy, where different kinds of signals combine to tell a more complete story. From GW170817, we learned that neutron star collisions are not only incredible fireworks displays, but also vital to the cosmic economy. They're the reason the universe has the ingredients needed to make worlds, and everything on them. But kilonovae don't always come from neutron star pairs. Sometimes a neutron star merges with a black hole. In these cases, the results are different, sometimes quieter, sometimes more violent, depending on the size of the black hole and the angle of the collision. If the black hole is too massive, it can swallow the neutron star whole without producing much of a light show. But if conditions are just right, it can tear the neutron star apart, creating a brief but spectacular kilonova. These neutron star black hole mergers are harder to detect, but they offer valuable insights. They tell us about the population of compact objects in the universe, the role of black holes in binary systems, and the limits of neutron star structure before collapse. Every merger is a new chapter in the story of stellar evolution, and a new opportunity to test the boundaries of physics. Even more intriguing, some theorists believe that in the moment two neutron stars merge, they may briefly form a hypermassive neutron star, an object so dense and massive that it can only exist for a fraction of a second before collapsing into a black hole. During that sliver of time, it might emit gravitational waves in complex chaotic patterns, offering us a brief glimpse into the physics of matter at its absolute limits. These moments are fleeting, but they leave a lasting imprint on the universe. The gravitational waves spread outward at the speed of light. The gamma rays race through space. The kilonova glows and fades, scattering heavy elements into the galactic neighborhood. And here on Earth we detect it, we decode it, we marvel at it. From our little corner of the cosmos, we watch these rare, brilliant collisions and learn about the past. Not just the past of distant stars, but our own cosmic ancestry. The iron in your blood, the iodine in your thyroid, the gold in your jewellery, it all began in places like this. Neutron star collisions are not everyday events. In a galaxy like ours, they may only happen once every 10,000 to 100,000 years. But when they do, they are spectacular. They are bright, brief, and full of meaning. They are proof that even in death stars can give, that even in collision the universe creates, that something as violent as a neutron star merger can lead to beauty, in the form of precious metals, new elements, and glowing clouds of light. So next time you see gold, or platinum, or any of the rare, heavy things we treasure on Earth, take a quiet moment to remember. These didn't come from the ground. They came from stars. Not just any stars, but the densest, most extreme remnants of stars locked in a slow, spiraling embrace that ended in a single, spectacular kiss. A kiss that shook space-time. A kiss that lit up the universe. A kiss that, quite possibly, made you. By now, neutron stars might seem like they've shown us everything. Crushing gravity, wild magnetic fields, time-warping rotations and explosive mergers. But in truth, we've only scratched the surface. At their core, quite literally, neutron stars may hide some of the strangest, most speculative forms of matter in the universe. This chapter is where things get wonderfully weird. You already know that neutron stars are made mostly of neutrons, which are the neutral particles found in the nucleus of atoms. But when you compress matter to densities far beyond those inside a normal atomic nucleus, several times higher in fact, neutrons themselves might not be the end of the road. They may buckle under the pressure and break down into their fundamental components, quarks. Let's start with the basics. Quarks are the building blocks of protons and neutrons. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. In ordinary matter, quarks are always bound together in groups. They don't exist freely on their own. But inside a neutron star's core, things may get so dense, so compressed, that neutrons dissolve and release their quarks into a sea of what's called quark matter. This hypothetical state is sometimes referred to as quark-gluon plasma, a substance that may have existed in the first microseconds after the Big Bang. In that ancient moment, the universe was hot and dense enough that quarks and gluons, the particles that hold quarks together, floated freely in a chaotic soup. As the universe expanded and cooled, these particles combined to form protons and neutrons, and ordinary matter was born. But deep inside a neutron star, we may find a return to that primordial chaos. If the pressure becomes high enough, quarks might no longer be trapped in individual neutrons. Instead, they could flow freely, forming a dense, frictionless fluid of up, down, and possibly strange quarks, an exotic version of matter called strange quark matter. Why strange, you ask? Because in addition to up and down quarks, strange quarks are heavier and a bit less common in normal matter. But under intense pressure they might become stable, and if that happens, the core of a neutron star could be made of this bizarre, incredibly dense form of matter. Some physicists believe that strange matter might be more stable than ordinary nuclear matter, And if that's true, it could have some wild consequences. For example, there's a theory that if a single droplet of strange matter, sometimes called a strangelet, were to come into contact with ordinary matter, it might convert it into more strange matter, like a subatomic zombie infection. One strangelet could, in theory, begin converting everything it touches, turning entire stars, or planets, into strange matter. That sounds terrifying, but don't panic. There's no evidence that strangelets are on the loose, and if they are, they're staying very quiet. Still, it's a fascinating idea, and one that pushes the boundaries of what we understand about the building blocks of reality. There are other exotic particles that might lurk in neutron star cores too. One candidate is the hyperon, a particle similar to a neutron but with additional quarks, like a strange quark thrown into the mix. Hyperons are heavier than neutrons and tend to decay quickly under normal conditions, but inside a neutron star's core, they might stick around and play an important role in the structure and behaviour of the star. Why does this matter? Because the composition of the star's core determines how it behaves, how much mass it can hold before collapsing into a black hole, how it responds to pressure, and how it emits radiation. If the core is made entirely of neutrons, there's a certain set of rules. If it's made of quark matter, or hyperons, those rules change. It's like trying to predict how a cake will rise, without knowing whether it's made of flour or foam. Some scientists even think that quark stars could be a separate class of objects entirely. These hypothetical stars, smaller and denser than neutron stars, would be made entirely of quark matter. They might form when neutron stars collapse further, but don't quite become black holes. If quark stars exist, they'd be even more extreme than neutron stars, with surface conditions that defy imagination. Detecting one, however, is tricky. From far away, a quark star might look very much like a neutron star. It might pulse, it might spin, it might emit X-rays or gamma rays. But subtle differences, like how quickly it cools or how it reacts during a collision, could reveal its true identity. Future telescopes and gravitational wave detectors may be able to spot these differences and help confirm whether quark stars are real. And then, because the universe loves to keep us guessing, there are even more speculative ideas. Some physicists propose that dark matter, the mysterious invisible substance that makes up most of the mass in the universe, might accumulate inside neutron stars. Over time, this dark matter could alter the star's behaviour or even trigger its collapse into a black hole. Others suggest that neutron stars might contain Bose-Einstein condensates, pion condensates, or kaon condensates, all exotic forms of matter that we don't fully understand but suspect might occur under the right conditions. It's like neutron stars are playgrounds for every weird theory physics has ever invented. They sit at the crossroads of gravity, quantum mechanics, particle physics, and nuclear science, pushing each field to its limits and demanding answers to questions we're barely able to ask. And here's the most incredible part. We may be on the verge of finding out. New observatories like the NICER instrument aboard the International Space Station are measuring neutron stars with unprecedented precision, trying to pin down their exact size and mass. These measurements help determine the equation of state, the relationship between pressure and density inside a neutron star, which in turn reveals what kind of matter they contain. Meanwhile, gravitational wave detectors like LIGO and Virgo are capturing the signatures of neutron star mergers. These waveforms encode detailed information about how neutron stars deform and bounce during collisions, offering new clues about their internal structure. All of this means we're inching closer to answers to questions like, what is the most stable form of matter? How does the universe behave under maximum pressure? What's hiding inside the densest objects that aren't black holes? Neutron stars don't just stretch our imagination, they stretch our theories. They reveal the limits of our understanding and point toward the mysteries still to come. And as we continue to study them, we may discover not just what neutron stars are, but what we are made of and what the universe might still become. Because in the end, strange matter, quark stars and hyperon cores aren't just strange for the sake of it. They are possibilities. whispers from the edge of known physics, waiting for someone to listen closely enough to hear them clearly. Neutron stars may seem like cosmic loners, born from the death of massive stars spinning silently in the cold, far from the bright lights of galaxies. But despite their isolation, these dense little remnants play an outsized role in the universe. In fact, they might be some of the most important objects out there when it comes to shaping our understanding of how the cosmos works. For starters, neutron stars are natural laboratories. We can't build anything like them on Earth. We can't replicate the gravity, the pressure, or the density in any laboratory. But neutron stars do it all the time. They show us what happens when you push matter to the absolute edge of its existence. When we study them, we're essentially running experiments in physics, but on a scale that no human-made machine could ever achieve. Through them, we can test the laws of gravity. Einstein's general theory of relativity has been confirmed in countless experiments, but nowhere is it tested more severely than on the environment of a neutron star. These stars are so compact that they significantly bend space-time. When two neutron stars orbit each other, the way they spiral inward, emit gravitational waves, and eventually collide gives us incredibly detailed data about how gravity works in the strongest fields we can observe. In fact, one of the earliest and most famous confirmations of gravitational wave theory came from observing a pair of neutron stars, the Hulse-Taylor binary pulsar. Over time, astronomers noticed that the two stars were slowly moving closer together, just as predicted by general relativity. The reason? They were radiating energy in the form of gravitational waves. No light, no sound, just tiny ripples in space-time, slowly draining the orbit. It was indirect proof that gravitational waves were real, years before we ever managed to detect them directly. Neutron stars also help us explore the nature of matter. What happens when you compress a neutron? What does the inside of a superfluid look like? How strong is nuclear matter when it's not just in a nucleus, but in an entire star? These are questions that neutron stars are helping us answer, not just with theory, but with observation. Their structure, how big they are, how heavy they are, how they spin, gives clues to the equation of state, which is the relationship between pressure and density inside the star. Different types of matter, normal nuclear matter, exotic quark matter, or even strange matter, produce different predictions. By measuring the size and mass of neutron stars with increasing precision, we're narrowing down the possibilities. One day, we may know exactly what kind of matter sits at the heart of a neutron star, and when we do, we'll know something new and fundamental about the universe. Neutron stars also affect the universe in more direct ways. When they merge, they create elements, the heavy ones like gold, platinum, and uranium. We've known for a long time that stars create many of the elements in the periodic table, but until recently we didn't know exactly where the heaviest ones came from. Neutron star mergers answered that question. These stars also serve as clocks. Pulsars spin with incredible regularity, and that makes them useful for keeping time. Some millisecond pulsars are accurate to within a few billionths of a second. If you had a network of these pulsars spread across the galaxy, you could use them like a cosmic GPS system. In fact, astronomers have proposed using pulsar timing to help future spacecraft navigate through deep space, far beyond the reach of Earth's satellites. But perhaps one of the most exciting roles for neutron stars is their use in multi-messenger astronomy, the new era of science where we observe the universe not just with light, but with gravitational waves, neutrinos, and other particles. Neutron stars are perfect sources for these signals. They flash in radio waves, explode in visible light, and vibrate space-time when they collide. They help us connect the dots between different forms of observation, building a more complete picture of what's happening in the cosmos. And while all of this is incredibly useful for scientists, neutron stars also have a more poetic role. They're reminders of how the universe recycles itself. A massive star lives for millions of years, shining brightly and forging elements in its core. When it dies, it collapses, not into nothingness, but into something new. A neutron star. That star may one day merge with another, creating a kilonova, spreading elements into space, seeding future stars, planets, and perhaps even life. In this way, neutron stars are part of the grand cycle of cosmic creation. They are not just remnants of destruction, but seeds for new beginnings. And by studying them, we see that even the quietest, densest, most extreme objects have a place in the ongoing story of the universe. They may be small, they may be silent. But neutron stars are everywhere, scattered through galaxies, pulsing away in the dark, and with every pulse, every flare, every merger, they whisper something more about how the universe works, and how we fit into it. Let's take a step away from the science for a moment. We've talked about how neutron stars form, how they spin and shine, how they warp time and space. But what would it be like to visit one? Not just observe from a distance, but to float nearby, gaze at its surface, and maybe, very carefully, imagine what it would be like to touch down. Of course, in reality, you'd be crushed, vaporized, and atomized in the blink of an eye. But this is a thought experiment, so let's pretend we're safe in a perfectly engineered pod, immune to radiation, gravity, and the strange physics of neutron matter. Just for tonight, as your ship approaches the neutron star, the first thing you notice is how small it is. This object, which weighs more than our sun, looks no bigger than a city. Around 20 kilometers across, about the size of a small island, yet holding the mass of hundreds of thousands of Earths. There's no atmosphere in the usual sense, no clouds, no swirling storms. The outer shell of the neutron star is made of compressed atomic nuclei, smooth, rigid, and unimaginably dense. From orbit it looks like brushed metal, maybe with faint patterns across the surface, signs of magnetic field lines or ancient crustal fractures. The colours you see aren't really colours in the normal sense. Most of the light it emits is in the X-ray range, far beyond human vision. Your ship converts this to something visible, bathing the star in ghostly blues and whites. The star's gravity is pulling at you, hard. Even though you're still hundreds of kilometers away, you can feel it in the ship's instruments. If not for your artificial gravity generators, which we're generously assuming exist, you'd be falling toward the surface at unimaginable speeds. The escape velocity is around 150,000 kilometers per second, which is more than half the speed of light. If you dropped a coin from a height of 1 meter, it would hit the surface in less than a microsecond and release as much energy as a bomb. You decide not to open any windows. As you drift closer, you notice something strange. The horizon of the star seems to curve upward. It's as though you can see more than half the surface at once. This is gravitational lensing in action. The star's immense gravity bends the path of light, allowing you to see parts of the surface that would normally be hidden. If there were a bright spot on the far side of the star, you'd still be able to see it, distorted and stretched around the edge like a funhouse mirror. Your onboard clock is ticking, but something feels off. And it is. Time itself is running differently here. Thanks to gravitational time dilation, every second near the neutron star passes more slowly compared to time back on Earth. For every hour you spend in this orbit, several more tick by on the home planet. You're not just visiting a different part of space. You're moving at a different pace through time. At a safe altitude, your ship holds position. Below you, the neutron star is rotating. Some of them spin slowly, once every few seconds. Others, especially millisecond pulsars, spin hundreds of times per second. If this one is on the faster end, the entire surface might be whirling beneath you like a compact record player, flickering with beams of radiation sweeping through space like a lighthouse. The magnetic field is intense. Your sensors are struggling to stay calibrated. A typical neutron star already has a magnetic field trillions of times stronger than Earth's. If you're near a magnetar, that number could climb into the quadrillions. That's a one followed by 15 zeros. The field is so strong it could distort the shape of atoms. Even with shielding, your ship's electronics are flickering, twitching, and occasionally showing system alerts that you prefer not to read right now, but you're curious. What lies beneath that crust? You aim an imaginary probe toward the surface. It dives through the outermost layer, just a few centimeters thick, where plasma and radiation swirl in a violent mix. Below that is the solid crust, made of tightly packed nuclei surrounded by a sea of electrons. A little deeper, and things begin to change. The pressure grows so immense that electrons are crushed into protons, forming neutrons. These neutrons start to drip out of the nuclei and form a dense neutron-rich fluid. Then comes the famous nuclear pasta layer, where the matter is squished into strange shapes, rods, sheets, blobs. It's nuclear matter behaving like cooked spaghetti. And beneath that, the superfluid core, neutrons flowing without resistance, a quantum liquid that carries heat and spin in ways we don't fully understand. At the very center, maybe, just maybe, something stranger still, a core of quark matter, or something else we haven't imagined yet. But back on the surface, it's eerily calm. There are no sounds in space, but you imagine the silence would feel louder here, not emptiness, but compression, like the weight of the entire star pressing in on itself. Occasionally the star might glitch, a sudden spin-up caused by a shift deep inside, a tiny hiccup in its perfect rhythm. You wouldn't see it, but your instruments would pick it up instantly. A jolt in the regularity of the pulses, a twitch in the star's posture. You spend a few more moments in orbit, letting the reality of this place sink in. A teaspoon of this matter would weigh more than Mount Everest. The gravity is so strong that time warps. The interior is made of matter in states not seen anywhere else in the universe, and yet it's just sitting there, stable, quiet, spinning in the dark. Eventually you pull away. The star shrinks in your viewport. It was never very big, but now it looks like just another speck in the blackness, still pulsing, still whispering. As you accelerate into the distance, your clocks slowly resynchronize with Earth time. Messages start to catch up with you, the familiar rhythms of home return. But something is different now. You've seen a place where physics is stretched to its limits, where matter folds in on itself, where gravity becomes a sculptor and time flows like syrup. You've looked into the eye of a collapsed sun and returned, and though you were never truly in danger, thanks to the protection of imagination and fictional science, you've been changed all the same. Because sometimes just imagining what it would feel like to stand in such a place is enough to shift your perspective, to make the universe feel just a little bit bigger, and to remind you that even in the smallest, darkest corners of space, there is wonder waiting to be discovered. For all their strangeness, the crushing gravity, the frozen time, the spaghetti-shaped atoms, neutron stars have managed to capture more than just the attention of scientists. They've also taken root in the human imagination, because when something is both beautiful and terrifying, both invisible and powerful, it tends to become more than just a physical object. It becomes a symbol, a character in our cosmic story. Neutron stars have made appearances in books, movies, television shows, video games, and even music. They might be obscure compared to black holes or supernovas, but they hold a certain mystique, partly because they seem like a paradox. A neutron star is, after all, a dead star that still pulses with energy, a corpse that glows, a remnant that spins with perfect timing. It's as if the universe couldn't bear to let go completely, so it left behind something small, dense, and unforgettable. In science fiction, neutron stars are often cast in dramatic roles. They serve as hazards to navigate around, sources of mysterious radiation, or even as gateways to other dimensions. Some writers imagine civilizations living on or around them, perhaps not biological beings, but machines or energy-based life that thrives under extreme conditions. Others use neutron stars as the engines of time travel or the heart of exotic starships. When a story needs something strange and powerful, a neutron star fits the bill. Perhaps the most famous fictional neutron star appears in Arthur C. Clarke's short story, Neutron tide, which delivers one of the most efficient jokes in science fiction history. Spoiler alert. It involves a spacecraft getting too close to a neutron star and only a piece of the ship surviving. A star-mangled spanner. That's the entire punchline. It's a pun. But it illustrates something important. Even a humorous take on neutron stars depends on the audience knowing that these objects are dangerous, extreme, and gravitationally merciless. But neutron stars don't just belong to science fiction. They've also made their way into poetry, art, and even philosophy. To some, they represent permanence, something left behind after chaos. To others, they symbolize transformation, the ability to become something new after destruction. You don't have to understand quantum mechanics to be moved by the idea of a star collapsing into something unimaginably dense, something that keeps spinning through the dark for billions of years. There's something deeply human about that image, a life lived brightly, a collapse, and then somehow a new rhythm, a quiet persistence. Even in popular culture, neutron stars have quietly found their place. They show up in the Star Trek universe, in episodes where ships orbit too closely or detect strange emissions. They're referenced in shows like Doctor Who, The Expanse, and even Futurama. In video games, neutron stars often appear as dangerous obstacles or mysterious celestial objects, a kind of cosmic spice sprinkled into the skybox to make the universe feel deeper, older, and a bit more unpredictable. And let's not forget how they inspire real-world wonder. You don't need to be an astrophysicist to feel amazed by the fact that a neutron star, just 20 kilometers wide, can spin hundreds of times per second and weigh more than the sun. That kind of contrast, tiny and heavy, fast and frozen, feels like poetry written in physics. People make art about neutron stars. They compose music inspired by pulsar rhythms. There are songs, paintings, and digital animations that try to capture the eerie elegance of these stars. And of course, there are the real recordings, or rather translations, of pulsar data, where the radio signals from these stars are converted into audible sound. The result is a kind of cosmic heartbeat, a ticking clock from across the galaxy, regular, steady, and utterly alien. One of the most touching stories involving pulsars comes from the Voyager missions. In 1977, NASA launched two spacecraft, Voyager 1 and Voyager 2, to explore the outer solar system. Each carried a golden record, a time capsule of human culture, designed to be discovered by any intelligent life that might one day stumble across the spacecraft. On that record was a diagram showing the location of Earth using pulsars as reference points. Each pulsar was marked by its unique timing signal, like a fingerprint. The idea was that any civilization advanced enough to find and decode the record could use the pulses to triangulate the origin, Earth, and the time of launch. In other words, we use neutron stars to write our return address on a message in a bottle, tossed into the cosmic sea. That says something about how we view these stars, not just as objects of study, but as part of a shared cosmic map. Reliable, predictable, useful, beautiful, and perhaps a little bit mysterious. Because even with all our observations, all our models, and all our data, there's still something unknowable about neutron stars. We don't know exactly what's inside them. We don't fully understand how their magnetic fields evolve, or how their interiors behave. They remain, in many ways, puzzles, waiting for us to get closer, to listen harder, to think more deeply. But maybe that's the best kind of symbol a neutron star can be. Not something with a neat, simple meaning, but something that invites curiosity. Something that spins quietly in the dark, asking questions through its very existence. Questions about death and transformation, about time and pressure, about what remains when everything else has fallen away. A neutron star is, in the end, a riddle written in mass and magnetism. And like all good riddles, it doesn't need to be solved right away. Sometimes it's enough just to know it's out there, pulsing, waiting, reminding us that the universe is full of things stranger than we've ever imagined. So now we return to the question we began with. What happens after a star explodes? We've travelled a long way since then. We've watched a massive star burn through its fuel and collapse into something impossibly dense. We've stood on the threshold of its gravitational pull, felt time slow, and imagined peering into its exotic pasta-shaped interior. We've seen it spin and pulse like a cosmic metronome. We've watched it hiccup, flare, crack, and collide, and we've followed its light and its gravitational whispers across millions of light years just to catch a glimpse of what remains after the brightest light in the sky goes out. And what remains is not an ending. Not really. A neutron star isn't just what's left after destruction, it's what emerges from it. A transformation, not a disappearance. A rhythm, not a silence. A question, not a conclusion. Because even after all the science, all the theories, and all the observations, these little stars still ask big questions. What is matter when it's crushed beyond recognition? What does gravity do at its absolute limit? What strange forms of physics are hiding just beneath that crust? Are we seeing the final state of matter, or just the beginning of something stranger? In the introduction, we wondered whether the universe would give us answers, or just more questions dressed in cosmic mystery. And now, at the end of this journey, maybe the answer is both. Neutron stars show us that even when something ends, something else begins, that there can be elegance in collapse, beauty in extremity, and even a kind of peace in the spinning heartbeat of a dead star. And as you drift off tonight, whether you're listening on your couch, curled up in bed, or looking up at the night sky, I hope you carry with you the quiet reminder that the universe is vast, full of endings, full of beginnings, and always, always asking the next question. Sleep well,